starting off with the invited speech by Dr. Barabara Villarni from the University of Westminster, United Kingdom.
Hello, can you hear me?
Yes, ma'am.
Okay, hi.
Hello.
Hi. So if it's okay, I can share my screen and I can start the presentation. Okay, can you see my, okay, great. Hi everybody, good morning. My name is Barbara Villarini. I'm from the University of Westminster, and today I'm going to talk about artificial intelligence for automatic organ reconstruction and morphological feature extraction from medical images. And we will see which is the impact on healthcare. So, regarding the outline of this speech, I would like first give you some information about my background. We will see some research projects I was working on, particularly focusing on the aim, the objectives, which are the challenges and the contributions. We speak about the methodology that we are using in order to achieve all these goals and current results and achievements. I would like also then to speak about future works and current works that we are actually starting to work on till drawing the conclusion. So this is me. I received my PhD in information engineering from the University of Perugia in Italy. I was working mainly on image and video processing, developing objective quality assessment and error protection algorithms for images and video. Towards the end of my PhD and for other years, I have been working also as a software engineering and researcher in one of the research company in Italy, focusing on innovative digital cinema application until 2013, when I moved in London, and I started to work as research associate at University College London. And here, for the first time, I use my expertise and my skill in to solve some medical problems. So I apply my skill in the medical field, and I've been working in one of the research center, the Center of Medical Imaging Computing, developing some application for the non-invasive treatment and biopsy of prostate cancer. Then around 2015, I get an academic position at the University of Westminster. And a couple of years ago, I received the Royal Academy of Engineering Research Fellowship. And during this period, especially during the fellowship that I had, a lot of the opportunity to delve in the medical field, applying what I learned also from my postdoc position in the medical field, in order to solve some challenging problems that I'm going to speak now in the next slides. So just to make an introduction of which is the problem that I would like to solve and would like to work on. In the last decades, medical imaging technologies has really revolutionized healthcare. You know that now we have detailed images of the anatomy of the human body, and the number of patients that undergo MRI, CT scan is incredibly high. You need to think that we acquired millions of abdominal images in the UK every year. However, most of the information that could be derived from a careful analysis of such large data set is neglected, mainly due to the fact that the available tools require interaction from radiologists and radiographer, who should analyze very carefully each slide in order to identify a specific pattern in the images that could indicate an early sign of specific disease. But of course, this required a lot of effort, a lot of time. Imagine that someone needs to go through all these slides, and when you undergo an MRI scan, I'm thinking that you have to think that an MRI scan has hundreds of images. So this work from a point of view of a person is quite difficult, it's not really feasible. So that's why we are using computational methods. Computational methods are able to analyze automatically a large medical data set. So in this way, we are able to provide unique opportunities to answer clinical and scientific questions, and would commence what we call a subject stratification according the organ morphology. So in this case, we can have chance to make studies in order to improve the analysis and the detection of disease and providing guidance for treatment planning. Of course, there are serious challenges in developing a robust automatic segmentation techniques. First of all, we have to deal with anatomical structures, and some of the organs have high structural variability in terms of size, in terms of structure, in terms of location of the organ. So if we consider here as example the pancreas is this yellow, light yellow organs here. It has a high structural variability among different persons. Also, the location within the abdominal cavity shifts from patient to patient. Furthermore, it lies behind the stomach and often overlaps with surrounding fat, vessels. Thus, it's quite hard to identify this organ through a full inspection. Another important challenge is related to different medical image modalities. Patients undergo medical scan based on different acquisition principles. You can think to CT scans, MRI, ultrasound. So we are dealing with different sequences. You can see here in these three images, three different acquisitions of the abdominal organs. We have a CT scan and two MRIs, which are acquired from different scanners. So you can notice that the MRI present additional age-based artifacts compared to the CT imaging. This is due to lower resolution and slower imaging speed. And furthermore, within the same medical modality, so I'm referring to MRI A and MRI B, we can see that there could be some differences due to the different scanners, different machine that we are using during the acquisition. And also, we may also have the presence of artifacts due to patient movements. So the task becomes to be quite challenging. A third important limitation, which is important to mention, is that there are some challenges due to the dataset limitations. So first of all, it's quite hard to have a very high number of images manually annotated that could be used to train the artificial networks, to train the AI system. You know that a low number of images during training can lead to low accuracy and high difficulty to test the model. So we need also to take into account this fact. So considering all these challenges, the contribution of the work should be develop a novel and robust automatic deep learning approach, so an AI approach for the automated organ muscle segmentation in volumes of medical images from different modalities. This approach is going to use, instead of 2D features learning, 3D volumetric information, so 3D features. We aim to have a framework which is modular, scalable, and generalizable in order to be used also for other applications. And in order to do so, we aim to evaluate the approach using different datasets, such as MRI, DCMRI. DCMRI is a digital contrast enhancement MRI, where a contrast agent is injected into the patient. And then we target distinct abdominal organs, for example, pancreas, liver, kidneys, and muscles, such as the iliopsoas muscles. And of course, in order to assess, we compare with state-of-the-art in order to also demonstrate the high statistical stability, given the difference in image quality among all these different modalities. And finally, our contribution to the scientific and medical community is to provide a web-based application to perform the automatic segmentation of organs, a web-based application that could be accessible and open source in order to foster collaboration and integration across different disciplines. So these slides shows at high level the proposed segmentation framework. So the idea is that from a radiological scan, we can obtain some prognostic biomarkers, which can be used to predict a condition or its progression. So the initial input is a 3D medical volume, as you can see, that goes through a segmentation process in order to get a 3D accurate reconstruction of the organ of interest. In this case, in this slide, you can see the pancreas. And the segmentation result is then processed through a biomedical model, which compute then all the morphological features for the final prediction of a condition or for the evaluation of its progression. But how do we automatically recognize the organ of interest within the medical image? So we are using deep learning approach. In this slide, I would like to provide the main concept. So we see that a deep learning network is trained using multiple image volumes and respective annotated ground truth of the organ of interest, in this case, the pancreas. So someone, a radiologist or radiographer, annotated manually the organ of interest. So the aim of the training process is to optimize the deep learning network in order to recognize distinguished features and boundaries of the pancreas. And the network is optimized by iteratively minimizing the error between the output prediction and the actual desired outcome, which is the ground truth. And we do so using a loss function through a technique that is called backpropagation, which updates the convolutional layers filter, minimizing the overall loss. So when then we go at the testing stage, an image volume, an unseen. So this image volume is something that we didn't use during the training, obviously during the training process. So this image volume is processed through the fully trained deep learning network, which performs a pixel-wise or voxel-wise prediction in order to generate the output as a sequence of 2D slice or 3D volume differentiated by pancreas and not pancreas labels. Now, if we want to delve a little bit more in detail, as you can see from this figure, the training stage simultaneously develops a network for localizing the organ of interest and the segmentation network to predict the labels that correspond to organ and not organ tissue. So if now we look at the localization stage, so we are looking at this first part, we downsample our volume and we feed it to a deep network that we call 3dBr unit. So this architecture builds upon a popular network used as a baseline for many medical segmentation tasks, which is called a UNET. So the UNET architecture consists of three main sections. We have the downsampling, which is also called encoder. We have the upsampling, which is also decoder, and we have a bottleneck, which is the bridge between the two sections. And every light blue block that you see in the figure represents a multi-channel feature map. All the white blocks represent the copied feature maps, and then the arrows represent the typical different operation in a neural network. So in the upsampling part, we have a large number of feature channels which allow the network to propagate context information to higher resolution layers. And building on the UNET architecture, we add residual learning blocks, which are using skip connection in order to have an original input added to the output of the convolutional block. And doing so, what we aim to do is to increase the number of connections within the segmentation network, improving the segmentation accuracy and optimizing the process, achieving a faster convergence. Now, this is about the localization. So if I go back, is this part of the diagram of this figure. The second part of the training stage develops a 3D tiramisu model using a uniformly cropped region where the organ of interest is fully present. So now, if we want to see the tiramisu network. So the tiramisu network, you can see the diagram in this image, extends the dense net architecture, which is particularly suitable for the semantic segmentation to work as fully convolutional networks by adding an upsampling path to recover the full input resolution. So we can note that in this case, the upsampling and the downsampling path are different. In the downsampling, the input to a dense block is concatenated with its output, leading to a linear growth of feature maps, whereas in the upsampling, we don't have this. And this approach allows to build a very deep, fully convolutional dense net without what is called feature map explosion. Now, I don't go too much in detail about the architecture. We have some papers where you can have a look to the details, and also all the code is open source and fully accessible. So for the testing, we are using unseen image volume. So for the testing phase, The fully trained 3DB unit performs a coarse segmentation of the target organs in order to find the bounding box to crop the volume containing the region of interest, and then the cropped volume will be the input for the 3D tiramisu model, which performs a fine and detailed voxel-wise prediction of organs and not organs. So we use a high amount of data for different organs and modality. We collected this data and we manually annotated through the help of expert radiologist and radiographer. So we can access to the following data set. As you can see, we have 6 different data sets of MRI, DC, MRI, and CT modalities, targeting different abdominal structures, such as the pancreas, liver, kidneys, and iliopsoas muscle. So in terms of what we get, in terms of result and evaluation, we consider the DSC, the dye similarity score, and the Jacquard index are metrics that represent an accuracy score of the overlapping between the segmentation and the ground truth. Now, in these slides, I provided the segmentation for the pancreas. As I said before, the automatic pancreas segmentation is an extremely challenging task due to the high structural variability of this organ and the similar grayscale intensity of nearby tissue. And the results are reported for 2 different MRI datasets where the data acquisition was made from 2 different scanners, and also 1 CT dataset, which is publicly available. So in the image, the segmentation outcome in green overlaps the ground truth in red, and with the corresponding dye similarity scores. And the results, as you can see, are compared with the state-of-the-art work using the same dataset, and what we obtain with the 3D proposed method outperforms state-of-the-art, achieving a high dye score. And also what we are looking for is to have low standard deviation, which demonstrates robustness towards variation of contextual information. We also show these results to an expert radiologist and radiographer in order to get some qualitative results, and both confirmed that the method produces detailed pancreas contouring for, they said, for every protrusion and indentation, as opposed to an approximate tracing of the organ, which is of paramount importance for an accurate analysis of the organ for making diagnosis for specific illness. The proposed approach is extended to a broader spectrum of MRI sequences and organs. You can see for each dataset 2 different medical scans with the superimposed segmentation outcome in green and the ground truth in red is proposed in this slide. In particular, I would like to note that the iliopsoas muscles, so the muscle in the abdomen, is an anatomical structure with high variability, and the kidneys dataset contain quite challenging data because it comes from a pediatric DC MRI dataset with clinical normal and abnormal kidneys with varying level of hydronephrosis, which is a condition where kidneys show irregular size, shape, and location. And the segmentation results continue to demonstrate, anyway, statistical stability despite a high variability. Now, using our dataset and apply the proposed framework, we want to compute some features, some morphological features. So We compute the volume and the curvature. The volume gives a measure of the organ dimension, while the curvature describes the organ surface and gives information about the level of smoothness and ruggedness, providing an indication about potential deformity of the organs. And this study that was carried out with the collaboration with life science school in our faculty had demonstrated that what was already been observed. So that in some subjects with the type 2 diabetes, the pancreas displayed an involuted morphology with serrated borders. So as you can see, this kind of study could help also to confirm some of the previous finding. Another study that has been carried out regards feature extraction from DCE MRI volumes from kidneys. As I said before, the kidneys in a pediatric population. This work was done in collaboration with Harvard Medical Schools, and the data are from Boston Children's Hospital. So we are targeting a specific patient with some specific disease. And using the proposed approach, we segment, so using the network that I showed you before, we segment the kidneys and we identify the kidney compartments, which are the medulla and the cortex, so medulla in red, cortex in green. And the accurate segmentation of the whole internal kidney regions can be used to extract clinically important markers of renal function that could optimize clinical decision-making. An example you can see in these figures. Here, the change in grayscale intensity over time can indicate the rate at which the gadolinium contrast agent reaches the kidney, and thus gives an insight into the condition of this organ. Moreover, it might be useful to explore a large scale analysis of medulla and cortex time intensity curves against corresponding DCE MRI scans in order to develop a method that guides the clinical classification of each kidney directly from the curves, and thus help to establish the probability of, for example, urethral obstruction in a quick way and in a non-invasive way. So these were some of the studies that we carry on, but the main idea is to provide also the scientific community with a web-based framework for the automatic feature extraction and segmentation of different organs in medical scans, using the algorithms, using this AI engine that I showed you before. So we develop a framework, we import all this functionality in an application which is open source and easily accessible by the research community. It's a web application developed in Streamlit, where the main features were uploading the medical scan, visualizing different views of medical scans, process these images through the AI model in order to perform the segmentation and in order to visualize, have a 3D visualization of the organs. Then we can extract some biomarkers and we implement also some utilities features. This is a demonstration of this tool. So I hope you can see the video. We can actually load we can load the image. In this case, I'm loading an MRI of the abdominal part. You can see we have 3 different views, the axial, the coronal, and sagittal, and through these slides, we can change the slides that we want to see. So we can see different positions of the organs. And then in this, we can also show metadata, because medical imaging If you undergo an MRI, you will get some DICOM file, and they hold some metadata information that can be extracted and displayed. They can hold also some patient information that obviously now has been hidden and not considered. We can here select which organ of interest we want to automatically see. In this case, I selected the liver, and you can see in each view the segmentation of this organ. Again, we can use the slide in order to change the position within the medical volume, and we can see the output. We can also get the 3D representation of the organ, ticking the box, and we can, for the time being, we can do simple thing, rotate, zoom in, zoom out, and then we can extract and save the 3D shape. And then if I go a bit further, otherwise it's too long, we can get some morphological features and download all the data that we got in a file. So the aim is to incorporate all these AI models into the development of an effective medical image analysis cloud-based application. So the aim is to make accessible this tool to clinicians, to scientists, medical care service, aiming to improve the process of diagnosis, analysis, detection of disease. So the idea is to extend this web application also with other works that we are carrying out recently. I didn't put this work in the presentation, otherwise it would be too long, but we are also working on tumors segmentation, especially for brain. And we are trying, and we are currently working on improving the visualization in order to increase the user interaction. So the objective is to use VR, AR devices for an immersive experience, and this could improve the analysis for a certain organ to have a better understanding of the current state of the health of a patient, the progression of the disease, and could also use for training purpose, for example. Also, another important thing that we are currently working on is on integrating the algorithms that I showed in a federated, decentralized system. Federated learning is instrumental in medical imaging as it allows to build a common, robust machine learning model without sharing health records, preserving the privacy. And of course, this is very important topic nowadays. In other words, federated learning allows training the model locally on user device without sharing raw data with a central server. And this preserves the user privacy and guarantees the data security. Also, it would allow to use more diverse data coming from different institutions, from different sources, different machines, increasing the number of data that we could collect, that we could not collect, but to use the number of data that could be used for the training. And as I said at the beginning of the presentation, to train the system with a large amount of data allows a more robust semantic segmentation, and we could also target different, wider data modalities. So I would like to finish the presentation speaking about the final goal of our research group, which is to build a digital twin. So a digital twin is a computed generated image of a person, usually in the form of an avatar, and this image can be used to replace a patient in a clinical setting or to help with research. The benefit of designing a digital twin in healthcare include the ability to improve patient care and research. For example, by creating an accurate replica of a patient's brain, scientists can study disease more accurately and could learn more in depth, and could also put in practice how the treatment works on human cells, seeing different modification. But how do we need, how to build, what do we need in order to build a digital twin? First of all, we need data from a large cohort of patients, as I said at the beginning. This information can be used to train the AI models offline that work together to build the digital twin. And second, we need data from the specific patient. This information is used to personalize the model and to create the digital twin of the specific patient. It prepares the model for inference and the treatment simulation. You can see here an example using the framework that I presented so far and that we developed, extracting the information that I showed you before today. So you can see the main idea is how an avatar can carry all the previous checks that have been performed, and the doctor would be able to visualize them in an interactive way and in a collective way, making a more informed assessment, obtaining also prediction, and choose the most suitable treatment plans. Additionally, by using digital twins as replacement for patients in real life, hospitals could also save money on personnels and could foster, of course, a research project. So to conclude, the concept of digital twins is currently emerging and is really revolutionized the way we approach patient care and medical research. By creating virtual replicas of individuals and their organs, we can gain a full insight into a personalized diagnostic, treatment strategies, and disease progression monitoring. And the integration of digital twin technology with the advanced AI opens new frontiers in precision medicine. We can enhance patient outcome, we can reduce healthcare cost. And as we move forward, it is essential to collaborate across different disciplines in order to invest, to develop on this and to take advantage of the potential of the digital twin in healthcare. And I would like just to conclude saying that embracing this innovative technology and considering also privacy and data security issues, we can think to a new way of providing healthcare, which is patient-centric, data-driven, and continuously evolving to meet the needs of every individual. I would like to thank, of course, University of Westminster, Harvard Medical School, and UCL that collaborate towards these projects. And with this, I conclude my speech. And if you have any question, I'm happy to reply.
Thank you very much, Doctor, for that valuable presentation and speech. I would like to take this time to apologize and highly appreciate your patience with us amidst your busy schedule.
No worries, it was great to be here.
Thank you very much. Have a good day, ma'am.
Thank you.